Welcome to video 3.5 on periodic trends. So if you have not done so already, get out your periodic table because we'll be looking at it again today, and we're going to look at the different trends on that table. So our periodic table was created a certain way. So in this video, we're going to look at more of those trends and the different properties on our periodic table based upon some values we're going to look at. This video is also going to cover the octet rule. We're going to understand what the octet rule is, why it's important, and how it influences the behavior of the atoms, meaning why are we going to make what kind of ions. Here are some vocabulary terms that we're going to learn along the way. Some of these I will define, some of these will be used in context. Again, if you have any questions, pause the video and check out Google. But our periodic table. Our periodic table was organized a certain way based on the atomic number and the electron configurations. Well, because of the electron configurations, because of the way this is organized, we can start to see certain trends on the periodic table, meaning we can see some generalities. For example, atomic radius. In a moment, you're going to learn that the atomic radius is simply the size of an atom. And one trend on the periodic table is that the atomic radius gets bigger as you go down a group and to the left. Meaning, if you look here on your periodic table at francium, francium is considered the biggest atom, and helium would be considered the smallest. So when we talk about trends, we're talking about generalities. We're talking about things either down and to the left or up and to the right. And so the four major trends we're going to look at today in this video are the atomic radius, the ionization energy, the electron affinity, and electronegativity. Atomic radius is simply the size of the atom. Ionization energy is simply the energy needed to remove an electron. So this is to remove an electron. Electron affinity is the energy needed to gain an electron. And electronegativity is the atom's ability to steal an electron. So this is size, lose an electron, gain an electron, and to steal an electron, if you want to make yourself a quick note. So as we look at the atomic radius, the atomic radius is a very simple idea, and it's pretty self-explanatory. Think about geometry. The radius is, again, half the diameter. So when we talk about the atomic radius, we're talking about from the distance from the inside of the nucleus to the outermost energy level. So again, the atomic radius is the distance from the inside of the nucleus, from the center of the atom, to the outside of the highest energy level that the electrons hold in. Now, how did scientists come up with this? Well, scientists did, and how they defined this was they took a diatomic and they turned all of our elements into diatomics, and then once they made this molecule of two hydrogens bond together, they measured the distance from the center of one nucleus to the center of another one, and then they simply cut that distance in half. So it's defined by half the distance between two nuclei of the similar atoms bonded together. And again, this is just an understanding we have to help us define the size of the atom. So it can be thought of as from the center of the atom, from the center of the atom to the outer end into the energy level, or is actually defined by the half the distance between two nucleuses of the same atom bonded together. When you look on your periodic table, we see again this is a great resource. If you flip your periodic table over, on the back you will find this key. 3 of the 4 trends we're going to talk about today are already listed and given to you on the periodic table on the back. So right now, if you look on the back, you can see the atomic radius. It's the number on the bottom of that little red box inside each symbol box. So again, our atomic radius can be found right here, here, and here. And so when we talk about those trends, you can easily find those values to verify those trends. What is the atomic radius, or what is the atomic radius trend? Well, atomic radius tells us that down here to the left is going to be the biggest atom, and the atoms up to the right are going to be the smallest. Now let's think about this in 2 parts. First of all, let's think about it as we go down the periods, or as we add more electrons to the energy level. It's pretty simple to understand that hydrogen would be smaller than rubidium. Why would hydrogen be smaller than rubidium? Because hydrogen only has 1 electron. Rubidium has 37 electrons. Hydrogen only has 1 electron in the first energy level. Rubidium has electrons in the 5th energy level. So first of all, as we go down a group, we can see that the atomic radius increases because there's more electrons, and those more electrons are filling up higher energy levels. Pretty self-explanatory. Now, the next thing to think about is how does a radius behave when it goes across a period, when I go from left to right? Well, you would think, with the same logic we used before, that if I went from 1 electron in hydrogen to 2 electrons in helium, you would think the atomic radius would get bigger. You would think the atom would get bigger because there's more electrons. And that's actually what we do not see. There's this thing called electron shielding, where basically when I add an extra electron to the 1s orbital, when I go from hydrogen to helium and I now have 2 electrons in the 1s orbital, those electrons create a bigger negative charge. So the 1s orbital has a higher negative charge. And the higher this negative charge, kind of like the bigger a negative magnet, the stronger a pull is going to be towards the nucleus or towards that positive magnet. So what we see here as we go from left to right, the atomic radius actually shrinks because as we add more electrons in the same energy level, the negative charge becomes bigger. That negative charge becomes bigger compared to the positive nucleus. And so these energy levels slightly pull in. So again, when we look at the trend, we see that the atomic radius increases down and to the left. As I go down and I go from right to left, my atomic radius increases. Or another way to think of this is rubidium, or on your periodic table, francium, is going to be the largest atomic radius. And helium will have the smallest atomic radius. The next trend is called ionization energy. You've already heard this term before. An ion is when a neutral atom has a charge because it gains or loses an electron. So when I have something like sodium, when he's neutral, will have 11 protons and 11 electrons. Well, when sodium loses an electron, he goes from having 11 electrons to 10 electrons, he is now going to become an ion. He is going to have a charge. How do you know when things are an ion? Well, because one, I'll either give you the protons and electron count, or two, you will see a charge, a positive or negative charge in the top right corner of the symbol. And so here you can see sodium with a positive charge because there's 10 electrons compared to 11 protons, and so we have an ion. Now the process of making an ion is called the ionization, where the ionization energy is the amount of energy we see when an atom loses an electron. So again, if I look at my periodic table and as I'm trying to consider ionization energy, down here it shows you on the bottom left the first ionization potential. So it's this red number right here. That's the measurement of the ionization energy right here. And it's basically a measurement of how much energy, or the energy change, I should say even, when an atom loses an electron, or when one was removed. So as we get started here, I've already mentioned this rule, octet, but we got to get it in a formal slide so you can go back and check it. The octet rule is this rule where it says that elements, just like humans, want to be stable. We want to be stable, we want to be content, we want to be full. You know, at the end of the day, if your belly is full, you had a pretty good day. And so the octet rule is the same idea. If at the end of the day, if an atom or an element can get a full outer energy level, they're going to be stable. They're going to be inert. They're going to be satisfied. And that's why we would use the word stable. So the octet rule simply says atoms want 8 valence electrons. Now remember, valence electrons are s and p orbital electrons in the highest energy level. And so what we're going to see here is we can begin to predict what kind of ions atoms will form based upon how many valence electrons they have. Meaning if something has 7 valence electrons, we can predict that they're going to want to steal 1 electron to get to 8. Or in the case of sodium, sodium has 1 valence electron. You see that guy out here by himself? So we can predict sodium is going to be a positive charge because he will lose that 1 electron to get a full outer shell. So the octet rule just simply says atoms want 8 valence electrons, and because of that rule, we see and we can predict with high certainty what kind of ions these elements will form, either gaining or losing those electrons. And we'll come back to this in a little bit as we get down there. But again, if you get on your periodic table and you look at these ionization energies, which is in the red, where it's called the first ionization potential, you will see some trends. If you were to map out those different energies on a chart like this, you would see the trend on the periodic table. So first of all, we see at the top of all these peaks that helium, neon, argon, krypton, and xenon, radon all have really high ionization energy. It means it takes a lot of energy to steal electrons from these elements. Now the question would be why? Why is helium and neon and so on have so much energy to steal an electron? Why does it take so much energy to steal an electron from these atoms? Well, the answer is because these guys are noble gases. They are already stable. They already have a full outer shell. And so in order to steal an electron from it, it's going to take a lot of energy because they are already content. They are already like where they're at in life and like the fact that they have a full outer shell. So the ionization trends. Ionization energy increases across the period, meaning as I go this way, it becomes harder to steal an electron. Why? Because again, all these elements want to become like a noble gas. They all want to be like a noble gas in their full energy level. So in general, as we move left to right, the ionization energy increases because to remove electrons from these atoms over here is very hard because they don't want to be thinking about removing electrons. They want to be thinking about gaining an electron. And so again, ionization energy decreases as you move down. Why does it decrease as you move down? Because again, it's easier to take away things on the bottom left. Or you can think of it the other way. Ionization energy increases as you move up. One other way to think about this is that the highest ionization energy is up and to the right. So who is it really hard to steal electrons from? It's really hard to steal electrons from helium. It's really hard to steal electrons from fluorine because, again, helium is stable, and fluorine actually is the opposite. He wants to gain electrons. And that's what electron affinity is. Electron affinity is the energy required to take an electron. So electron affinity is the energy change to take an electron. On your periodic table and on this slide here, you can see that some electrons are easy to steal or to take an electron, and some don't. So electron affinity just shows us who is wanting to take an electron and who does not want to take an electron. When you think through this, again, think of the octet rule. What must an element do to have 8 electrons? If it takes, if they're very close to stealing an electron, then the energy change will reflect that. So again, those with 7 valence electrons are more likely to gain electrons, meaning they want to lose one. So again, these guys will have a high electron affinity because they're going to want to steal one. Now, in a similar way, when we see the trend here, this trend also increases to the up and to the right. You will notice on the last slide, I'll give you an overview. But all the trends, ionization energy, electron affinity, and electronegativity, all increase up and to the right. Atomic radii is the only one that's opposite. Atomic radii will increase down to the left. And you'll see that in the last slide. But again, this tends to increase as we go up a group. And the electron affinity is the highest up and to the right. So again, fluorine has the most to gain, has the most energy change to occur when it comes to taking an electron, because he wants an electron. So as we pause real quick and we're talking about ions with ionization energy, electron affinity, there's a couple other vocab terms you need to know. Ions can be broken down into 2 categories. We have cations and anions. Cations are positive ions, meaning that they lost an electron. Anions are negative ions, meaning they gained an electron. So again, something's a cation if it has a positive charge. How did it get to a positive charge? Well, it lost an electron. Anions are things with a negative charge. How did they become anion? Because they stole an electron. They stole an electron. Again, these will form based on the octet rule. Do things have to gain an electron to have 8 valence electrons, or do they lose an electron to have 8 valence electrons? And again, the 8 valence electron is called the octet rule. And again, we can think about what happens to the radius as these electrons get added. Again, obviously, just like the atomic radii, when we add electrons into a new energy level, we can increase the radius, or if we lose electrons energy level, we can shrink their radius. But also the electron shielding occurs too. When you think about chlorine here, we are going to gain an electron, and as I gain that electron, that anion is going to be slightly bigger because I'm adding another electron. All right, so now let's practice real quick. Let's get into some practice. This slide I added in here, so you just want to make this little note on your notes, and it's a way to practice coming up with ions. So for this first list here, I want you to, and I'll teach you how to do the first one, and you can try number 2, 3, and 4. But I want you to show me the ion as a symbol, and then tell me, is this an anion or a cation? So as we look at lithium, and you get your periodic table, you see lithium, if it's neutral, has 3 protons and 3 neutrons. So lithium, atomic number 3, 3 protons, 3 neutrons. Well, if lithium only has 2 electrons, what would its symbol be? So again, if it has 3 protons and only 2 electrons, we are going to see that lithium has a positive charge. And so you would write like this, and this would actually be a superscript, which I don't have that quick button here. There we go. I like it. All right, so again, how did lithium be written as lithium with a positive charge? Because I said he's lithium with 2 electrons. We know he has 3 protons. That's why he's called lithium with only 2 electrons. That's why he's a positive charge. Now, question is lithium positive, an anion or a cation? And you would be right to say that he is a cation. Okay? All right, so now let's look at fluorine. Go ahead and pause the video and try these yourself and see if you can figure out what the symbol would be for these 3 elements and if they'd be cations or anions. Pause the video and then I'll show you the answer. All right, so we see fluorine would have a negative charge. Fluorine has 9 protons with 10 electrons, so it would be fluorine negative. Calcium has a total of 20 protons, and since he has only 18 electrons, he would have a calcium plus 2 charge. And then sulfur, you would see, would be sulfur negative 2. Again, sulfur has a total of 16 electrons, 16 positive protons compared to 18 negative electrons, means you have negative 2 charge. So all we're doing is we're comparing the protons to electrons, and that's how we got these charges. Again, he would be called an anion, and then he would be called a cation, and then here, sulfur would be called an anion. Why? Cations have positive charges, anions have negative charges. Now, the other thing you're going to be able to do is you're going to be able to look at your periodic table and you can predict the charges elements would have. So again, all these elements want to become like a noble gas. They want to have energy levels that are full like a noble gas. So if I look at boron, we ask the question is how can boron get a full outer energy level? Well, thinking back to your electron configuration, you see that boron has 1, 2, 3 valence electrons. 1, 2, 3 valence electrons. 2 in the 2s and 1 in the 2p. So how will boron become like a noble gas? Well, boron has 2 paths to become like a noble gas. He can either gain electrons to become like neon, or he could actually lose electrons to become like helium. So if I'm boron, I have 2 options. I either gain 5 electrons or I lose 3 electrons. And the question is, which one would boron do? Which would be more likely? Which one would create less energy to do so? And the answer would be boron will develop a positive 3 charge, meaning boron is much more willing to lose his 3 electrons to become like helium with his electron configuration than he is to go out and to find 5 different electrons to become like neon. So for the first answer here, if I look at boron, boron would most likely have a charge of +3. I could write B with B with the +3 in the top right corner if I want to write the symbol for that. All right, now pause the video and go ahead and try to look at oxygen, potassium, chlorine, and see if you can predict their charges. All right, welcome back. Let's look at oxygen. What kind of charge do we predict oxygen will have? Oxygen is right here. Oxygen wants to become like a noble gas, so he could either, again, lose 6 electrons to become like helium, or he could simply steal 2 electrons to become like neon, and that is what he's going to do. Oxygen will often have a charge of -2. Now, one quick little shortcut here. Again, you can see on this corner right here above the O is what's called the oxidation state. I've already mentioned this in other videos, but the oxidation state kind of tells you what kind of charge that these elements can have, and so that -2 is actually given to you right there. But why? Why is oxygen -2? Because he will steal 2 electrons to become like neon. All right, potassium. Let's get through these quickly so we can wrap up this video. Potassium, he's going to have a +1 charge. How do I know that? Because potassium could either gain 7 electrons to become like krypton, or he could simply lose his electron to become like argon, and that's what potassium is going to do. Potassium will lose the 1 electron to become like argon, and potassium also has that +1 right here as his oxidation state. So potassium would be +1, and then chlorine you will see is -1. Why is chlorine going to have a ion as -1? Because again, chlorine is right here. Chlorine will want to steal 1 electron to become like argon, and that is the most common ion charge that chlorine would have. A couple more things about looking at charges. All of these groups have the same number of valence electrons, so we see this trend as well. These guys will always be stable, and so they won't form ions, but fluorine and down will always want to form a -1 ion. Oxygen will want to form a -2 ions. So oxygen, sulfur, selenium will form -2. Nitrogen and down will form -3. Carbon can go either way. Carbon, silicon, germanium, all these guys will either go +4 or -4. Boron will go +3. Beryllium and below will go +2 on their charges. And hydrogen through francium will go +1. Now, those are not absolute certain, but that's about 95% of the time. If you follow those trends going up and down the groups, you will find the right ion charge. All right. So last thing to look at as we wrap up is this thing called electronegativity. The electronegativity is just an atom's ability to steal an electron. Here's a little cartoon here. This atom is stealing 2 electrons, and these 2 female electrons are falling for him. And so they are being sucked into his pool. So electronegativity was actually a measurement created by a guy named Linus Pauling, and he basically just went through the whole table and he was measuring each atom's ability to steal an electron. I think of it kind of like the weight room. In the weight room, which kid bench presses the most? And so whoever has the highest electronegativity is like the highest bench press number, because when it comes to stealing things like someone's snack cake or someone's lunch, whoever bench presses the most can usually rip that away from somebody else and steal their snacks. So electronegativity is strength. It's a strength to steal an electron. And so the question would be is, when you think about your periodic table, who do you think would be the toughest? Who do you think would fight the hardest to steal an electron? So as you look on the periodic table, think of it in 2 different ways. First of all, does your noble gases, do they want to steal electrons at all? No, they do not want to steal electrons because they're already stable. So now let's think of it compared to fluorine to francium. Francium has 1 electron in its outer shell. Fluorine has 7 electrons in its outer shell. So between fluorine and francium, who do you think would have the most intense, passionate fighting power to steal an electron from somewhere else? Not francium. Francium doesn't want to steal electrons. He wants to lose his electron. Fluorine, however, does want to. And so we see fluorine actually has the highest electronegativity, and we see electronegativity increases up and from the left to the right. So you can actually see that on this next slide here. As I pop down here, the electronegativity trend. This guy right here is fluorine. He has the highest electronegativity. Again, if you look on here, electronegativity is down here in the top right corner. It's called Linus Pauling's electronegativity. But then basically, fluorine has the most to gain by stealing electrons. So those with 7 electrons will have a really high electronegativity, and we see this trend goes up and to the right. So again, I hope this video helped you out. I hope it wasn't too long. I haven't seen the time on it yet, but I apologize if it is. But again, in this video, the arrangement of the periodic table is there to show us the trends. Those trends that we see is we see atomic radius increases down and to the left, meaning that francium is the biggest atom out there. Ionization energy is the highest up and to the right. Ionization energy, again, is the energy that takes to remove an electron. So when I get high up and to the right, like fluorine and helium, those guys do not want to lose electrons, so it takes a lot of energy to steal their electrons. So ionization energy is highest up and to the right. Electron affinity is the energy to gain an electron. So again, we see that's up and to the right. And the electronegativity is the actual fight, the strength. So electron affinity is an energy measurement. This is something we came up in the lab. Electronegativity was Linus Pauling's idea, and it was his relative strength of saying how strong, how much will elements fight for an electron. And again, electronegativity is the highest up and to the right. Have a great day.